first of all introduce myself. I'm Dr. Poonam Tiwari. I'm a scientist here at Indian Institute of Remote Sensing. And today we will be discussing about image enhancement. So I welcome all of you in this session of digital image processing, and today we are going to talk about image enhancement. So by now you must be aware of what is a digital image, how a digital image looks like, that a digital image is made up of pixels. These pixels are arranged in form of rows and columns. Each pixel has a number associated with it, and that number is known as digital number. This digital number is a record of the amount of energy emitted, reflected, or backscattered from that part of the ground. Okay, so in short, what we can say is that a digital image is an array of numbers. Okay, so now we can play around with this array of numbers, and this modification of numbers, of the digital numbers, so that the effect of image on the viewer is changed. That means the impact of the image is changed. The visual impact of the image is changed. That particular modification of the pixel numbers is known as image enhancement. So image enhancements are generally used so that the image becomes more appealing visually. We can do more interpretation out of this image, and we can have a better understanding of the features that are present in the image. Image enhancement is done after the image is corrected from all sorts of distortions. So in the previous sessions, you must have read about the distortions, the geometric and radiometric distortions. There are certain geometric and radiometric errors. What are these errors? How we can correct these errors? So you understand those things now. So after all that corrections are done, the image enhancements are carried out. So image enhancement is the process of making an image more interpretable for a particular application. Now please focus on the term for a particular application. So that means image enhancement for a particular application would be different from image enhancement for another application. So if for the same image, if I want to extract the features, water features, I would apply different type of enhancement. If I want to enhance the land features, I would apply different type of enhancement, and so on. Now, why is it so useful? Because when you look at the image, raw image, you would observe, or you would understand that the data in the raw image has a very poor contrast. Okay, so to improve the contrast of the image and to make the image more interpretable so that we can get more and more information out of the image, we apply this particular technique. Okay, so as I have already discussed, that it is done after the image is corrected for all sorts of distortions. Another thing is that the image enhancements can be done temporarily on the image, or permanently also you can do image enhancement. Now, if we want to categorize these image enhancements, the image enhancements can be classified into 3 different categories based on how they are performed, and they are namely radiometric enhancement, spectral enhancement, and spatial enhancement. So today we will be talking about all these 3 types of enhancements. So when we are changing the brightness value of the pixel or grace level of the pixel independently, that means without using the information from other bands, without using the information of the surrounding pixels. So we are taking the original pixel value, and based on certain formulas, we calculate the new pixel value. Such type of enhancements are called as point operations. For calculation of new brightness value, if we are going to utilize the pixel values of the surrounding pixels also, then such type of enhancement is known as spatial enhancement, and it is also called as a local operation, because the pixel values or the information content of the surrounding pixels or surrounding neighborhood is also taken into account. The third type of enhancement is a spectral enhancement. So if we want to if we are calculating the new brightness value using the brightness value of a pixel in 2 or more than 2 bands, then such type of enhancement is known as spectral enhancement. So we will start discussing these enhancements one by one, and we will start with radiometric enhancement. So as we have already discussed that it is the modification of brightness values of each pixel in an image dataset independently. That means the original brightness values would be used to calculate the new brightness values. So radiometric enhancement, it brings out the contrast of the image. It is applied to all the bands separately. The radiometric enhancement or stretching that we apply on one band may not be applicable to the other band. So for every band, the enhancement has to be done separately. So contrast enhancement, which is a very popular enhancement technique, falls under the radiometric enhancement. So before going into the details of contrast enhancement, let us first try to understand what do we mean by contrast. So contrast means the amount of difference between average gray level of an object with that of its surrounding. So if the difference between pixel value of object and surrounding is more, then the object is more discriminable from its surroundings, and if the pixel values are similar, then the contrast is less and the object is not identifiable from its surroundings. So we can also say how washed out an image appears or how vivid an image appears. Mathematically, if we want to describe contrast, contrast would be the ratio of maximum gray level value to the minimum gray level value in the image. So if the contrast of the image is more, then it is easier to interpret the image. As you can see here, I have shown a false color composite. So I'm aware that on your screens, this false color composite, you must be observing completely black in color. So why this is a raw image, and why does such type of thing happens? So I have displayed the histogram of 3 different bands, 4, 2, and 1, the same bands which are used, which have been visualized here in the viewer. Okay, so in all the 3 histograms, you can see that the majority of data is lying in a very narrow range, such as in band 4, it is lying between 0 to 58. In band 2, it is lying between 0 to 34. And again in band 1, it is lying between 0 to 54. And even in that range, many areas are such in which a very few number of pixels are there, so you are not able to visualize them on the histogram. So very less number of pixels are there. So because of this narrow range of distribution of the brightness value, the contrast of the image is poor. And because of this poor contrast, we are not able to interpret many features on the image. So you can see here, I have shown a low contrast image and a saturated image. So a low contrast image, all the brightness values are compressed in the lower part of the histogram, whereas in a saturated image, the histogram is towards the brighter part, and that is why lot of brightness is there, but that also is not good for interpretation purpose. So the first image, in which the histogram is evenly distributed throughout the range of display device, that is 0 to 255, such type of data, such type of visualized image is good for interpretation purpose. So coming back to radiometric enhancement. So radiometric enhancement can be divided into two broad categories: linear contrast enhancement and non-linear contrast enhancement. So in the linear contrast enhancement, there is a linear relationship between input and output brightness values. Whereas in the non-linear contrast enhancement, it does not follow a linear relationship. So there are variety of linear contrast stretching algorithms. Some of them are minimum maximum stretching, percentage stretching, standard deviation stretch, piecewise stretching, then sawtooth stretching. Whereas in the non-linear contrast stretching, the major algorithms are logarithmic, inverse logarithmic, exponential, or what we can say is you can apply any kind of mathematical and trigonometrical function here and can generate a non-linear contrast enhancement stretching. So we will start discussing the linear contrast stretching, and we will start with the basic one, that is minimum maximum stretching. As the name itself is suggesting, the density values or pixel values in the scene are literally pulled farther apart, that is expanded over a greater range, exactly like a rubber band or like an elastic band. So you bring the dark part of the histogram, the darkest pixel of the histogram, to 0, and the brightest pixel of the histogram to 255, and all the values in between values are the new values are calculated for those values in a linear manner. So it expands the original input values to make use of total range of sensitivity of the display device. The effect is to increase the visual contrast between two areas of different uniform densities. This enables the analyst to discriminate easily between areas initially having a small difference in density. So as we have already discussed, that a DN value or pixel in the low range of original histogram is assigned to extreme black, is given a new value as 0, and a pixel in the brighter area is assigned to extreme white. The remaining pixel values are distributed linearly between these two extremes. So as you can see here, in the input data, the pixel values were ranging from 84 to 153. So after stretching, the pixel with 84 value has been now brought to 0, and with 153 value is now brought to 255. And all the in-between values are stretched linearly to fill in the entire range from 0 to 255. If we plot a graph between the input brightness value and output brightness value, we will observe that there is the graph is linear. Okay, the relationship between these two is linear, and it follows a straight line equation. So using the given formula, we can calculate the new brightness value of the pixel. So new brightness value Y would be X minus X minimum divided by X maximum minus X minimum multiplied by 255. Okay, so you just put in the pixel value and it will give us the new pixel value. So these type of enhancements are best applied to remote sensing images with Gaussian or near Gaussian histograms. So I have shown you a few images on which such type of stretching has been applied. So you can see these are the moon images, and the stretching has been applied on these images. On the previous, in the original image, the features are not distinguishable. Many features are being left out, whereas when we stretch the image using minimum maximum stretching, so the more and more features become distinguishable in our image. Similarly, here also you can see this is unenhanced image and stretched to minimum maximum value. Here also, so I have zoomed into an area and shown you how the things are changing, how the features are now more identifiable. Okay, so this again is using minimum maximum stretching, and this is the stretched histogram. Okay, so these are some of the examples how after applying minimum maximum stretching, the contrast in your image will improve. So you can see here also. Okay, now the second type of radiometric enhancement is percentage cutoff stretching. So it is similar to minimum maximum stretching. The only thing is that we are not going to use the minimum and maximum of the input brightness values. Instead, we take a certain percentage of pixels. Suppose I say we will enhance 95% pixels or 98% pixels. Okay, so from the mean of the histogram, 49% on one side and 49 on the other side. So these many pixels, wherever the minimum and maximum value is coming, those many pixels we will enhance. Okay, so percentage linear contrast stretching is similar to minimum maximum stretching, except that this method uses a specified minimum and maximum values that lie in a certain percentage of pixels from the mean of histogram. So similarly, similar to percentage cutoff stretching, we have standard deviation linear stretching. So from the mean of the histogram, we can select one histogram, two histogram, or three histogram. So wherever these 2 or 3 histogram lie, so those many pixels we will enhance. So this type of stretching is used to push the tails of histogram beyond the original minimum and maximum values. So for some minimum, digital numbers, the contrast is lost, whereas for others, the contrast is enhanced. So these are some of the results of minimum, maximum, and standard deviation stretching. So you can see how the comparison can be made. So in the minimum maximum, the original minimum and maximum values are used, whereas in the standard deviation stretching or in percentage stretching, a set amount of pixels are stretched. Okay. So this again, for the same example, I have shown you the enhanced image, the original raw image, minimum maximum stretching, and when we are stretching it to 99%, Okay, you see how much difference it has made. 100%. The image was appearing hazy and many features were not identifiable. Whereas when we have put that as 99% stretching, we are losing the information of 1% pixels, but still for the other pixels, the contrast is highly improved now. Okay, so this is standard deviation or percentage cutoff linear stretching. Another radiometric enhancement technique is piecewise linear stretching. So when the distribution of histogram in an image is bi or trimodal, the analyst may stretch certain values of the histogram for increased enhancement in selected area. A piecewise linear contrast enhancement involves the identification of number of linear enhancement steps that expands the brightness ranges in the modes of the histogram. So, what is done is in piecewise linear stretching, a small series of minimum maximum stretches are set within a single histogram. So we divide the area into small parts and then apply minimum maximum stretching in those areas differently, independently. So the same data, we have applied minimum piecewise linear stretching here. Now coming to non-linear contrast enhancement. So as the name itself is suggesting that the relationship between the input and output brightness value is a non-linear function. Okay, or what we can say is the output brightness value, which is represented here as y of x. Y is equal to is a function of is a non-linear function of x, where x is the input brightness value. So it increases or decreases contrast in different regions of histogram. So based on your requirement, you can select which particular type of enhancement you want to apply. So some common non-linear contrast enhancement methods are logarithmic, inverse logarithmic, square, square root. Within this statistical category, we have a very important stretching that is histogram equalization. We can also apply some trigonometrical functions also. So what is a logarithmic contrast stretch? So all these non-linear enhancement methods are two-step process. In the first step, the non-linear transfer function is applied on the original pixel values, and in the second step, the output values are stretched linearly between 0 to 255 using minimum maximum stretching. Okay, so in the logarithmic contrast stretching, the logarithmic values of input data are linearly stretched to get the desired output values. It is a two-step process. In the first step, we find we calculate the log values of input dn values. In the second step, log values are linearly stretched to fill the complete range from 0 to 255. So as you can see here in the graphs, the logarithmic stretch, the transfer function shows that the maximum slope is in the lower part of histogram or darker brightness values. So we will conclude here that for logarithmic stretching, the dark part of the histogram would be enhanced to maximum level. Now, another very important method of nonlinear contrast enhancement is histogram equalization. So in histogram equalization, the histogram of the original image is redistributed to produce a uniform population density. This is obtained by grouping certain adjacent gray values. Thus, the number of gray levels in enhanced image is less than the number of gray levels in the original image. Contrast is increased at the most populated range of brightness value of the histogram or peaks. It automatically reduces the contrast in very light or very dark part of the image associated with tail of normally distributed histogram. So to explain this histogram equalization, we can have an example of a hypothetical image, and this hypothetical image has brightness values from 0 to 7, 0, 1, 2, 3, 4, 5, 6, and 7. So for every brightness value, there are certain number of pixels that are assigned to that particular brightness value, such as in this case, the table indicates that 0 brightness value frequency is 790. That means 790 pixels have a brightness value 0. Okay, 1023 pixels have brightness value 1. Now, what we will do is we will calculate two parameters here. One is Li and one is Ki. So Li is simply brightness value divided by the maximum brightness value. So 0 divided by 7 is 0, 1 divided by 7 is 0.14, and so on. 7 divided by 7 is 1. Another thing that we will calculate is cumulative frequency transformation function, which we represent as Ki. So Ki is the frequency of this class divided by cumulative frequency of this class divided by the total frequency. So cumulative frequency means that frequency of this class plus frequency of all the classes above this particular class. So 790 divided by 4096, then for brightness value 1, it would be 790 plus 1023 divided by 4096, and so on. So now Ki and Li values have been calculated. Now we will redistribute our histogram in such a manner that we will find out the correlation between the Ki and Li. So which Ki, for this particular Ki, which Li is having the least difference. So all the pixels belonging to this particular class will be now distributed or will be now shifted to the new category, such as the Ki for class 1, which was 0 brightness value, is 0.19. It is closest to Li of class 2, which is having brightness value of 1. So based on this, so all the pixels, 790 pixels, which were earlier having a value of 0, will now be shifted into class 1, the class in which the pixel value has a value of 1. So all these 790 pixels will now have pixel value as 1. So such type, in this way, the equalized histogram is generated. As you can see here, the equalized histogram is showing that many categories at the tail end of the histogram have been merged into single class, whereas the distance between the most populated area of the histogram has increased. So histogram equalization, it increases the contrast in the most populated part of the histogram. So this is again a few examples of unstretched image, linearly stretched, and histogram equalized stretch. So you can see by histogram equalization, the major areas of the image, the contrast has improved. Okay, the same moon images have now been up, histogram equalization has been applied, and you can see such type of features now which were not visible in the minimum maximum stretching. Those features are also now more visible. Okay, so many more examples of histogram equalization. You can see here, this is again histogram equalization on different bands of data. Another technique of is histogram matching. In histogram matching, we are trying to manipulate the pixel value of one image into the same pixel distribution as another image. Now, what does this do is when we are going to do a big project in which we have to mosaic multiple images, then the histogram of one image would be different from its adjoining image. So during the mosaicing, what will happen? The clear-cut line, the seamless mosaic we will not get. There would be a line appearing wherever these two images are mosaicked. So to avoid such type of thing, we do histogram matching, in which we take one image as master image, and the histogram of the second image is changed as per this image, as per the master image. So this is histogram matching. Another method is Gaussian stretching, in which stretching is based on the histogram of pixel values. In Gaussian stretch, the observed histogram is fitted to a normal or Gaussian histogram. And this again, Gaussian stretching, it highlights the tail part of the histogram. Now, density slicing is also one technique which is sometimes represented as image enhancement technique. In density slicing, we can slice our histogram into various areas, and for every area we can assign a different color so as to make the features more interpretable and the image more visually appealing. So as you can see here, in this image, we have created the density interval from 76 to 84. It would be bright green, 85 to 93 dark green, and so on. Okay, and the net result is available to you. So this density slicing is done for temperature image. So such type of density slicing is for thermal images. It is quite common to show which objects are having a higher temperature and which objects are having lower temperature. Now coming to the next part of the presentation, that is spatial enhancement. So before going into the spatial enhancement, we should also try to understand what is spatial frequency. Spatial frequency refers to radical variation in the grayscale. So if in an image or in an area, the pixel values are abruptly changing, then such in such area, we say that the spatial frequency is more. And if the spatial frequencies are slowly varying, are changing, but they are changing slowly, then we say that the spatial frequency is low. So rough textured areas of the image where the changes in tone are abrupt over a small area are called as high spatial frequency areas. So if we want to define a spatial frequency, it would be the number of changes in the brightness values per unit distance for any particular part of the image. So in an image, we generally have both type of details, low frequency details and high frequency details. Okay, so we will see this is a rough textured image, and this is having a high spatial frequency, and this is a low smooth image which is having low spatial frequency. Below I have shown 3 examples, one of 0 spatial frequency, that means all the pixel values are same. Low spatial frequency in which the values are changing, but it is changing at gradually. And high spatial frequency is where the change in brightness value is abrupt. So this is a remote sensing image, and where we can see that where are the low frequency and high frequency details. So I have zoomed in an area. You can see the homogeneous areas in which all the pixels are having similar brightness values. That means the homogeneous area in which there is only forest. Okay, so such type of homogeneous area will be having low spatial frequency, whereas the heterogeneous area or the areas in which the boundary of features is appearing, such type of areas are having high spatial frequency. So all the edges are having high spatial frequency, and the area at the center of the feature is having low spatial frequency. Now coming to spatial filtering. So spatial filtering is the process of dividing the image into its constituent spatial frequencies and selectively altering certain spatial frequencies to emphasize some image features. Or we can say that spatial filtering is the process of suppressing certain frequencies and passing the other frequencies. It increases the analyst's ability to discriminate the details. It is a local operation, that is pixel value is modified based on the value of surrounding pixel also. So it is used for enhancing certain features. It is used for removal of the noise and removal of salt and pepper effect from the image. So many things are there. So filters are used for spatial filtering, and the filters are the algorithms which we use for filtering. The filter is composed of a kernel or window mask or convolution mask, generally 3 by 3, 5 by 5, 7 by 7 and 9 by 9. You can have any size of window mask, but it is an odd numbered mask. So 3 by 3 we will and this we are doing so as to get the central pixel. If we have an even numbered mask, so we will not get the central pixel. Okay, it is a square mask, the equal number of rows and columns. And the second thing, one is window mask, and the second thing is the weights or constants that is given to the mask. As you can see here, this is a 3 by 3 window or convolution mask, and the weights that we have provided are 1, 1, 1 and 1, 1, 1, 1, 1, 1. So all the windows, all the filters, they are having a weightage of 1. So now coming to the filtering. So in the convolution or filtering operation, the brightness value at a location in the output image is a function of some weighted average of the brightness value located in a particular spatial pattern around ij location in the input image. So how it is done is, we will take the filter, we will take the window mask and put it on certain part of the image. Now, in the second step, the central pixel value is to be calculated based on the neighboring pixels. And how it is calculated? The weight given to the window mask is multiplied by the brightness value at that location. So C1 multiplied by BV1, BV stands for brightness value. C2 multiplied by BV2, C3 multiplied by BV3, and so on. We sum up all this and get an average of this. Okay, so if the brightness value 5 and this value that we are getting, it will be the new brightness value of the central pixel, the 5th pixel here. Okay, so for this central pixel, the brightness values are calculated. Now the central value is replaced by the new value and window is shifted by 1 pixel to the right and the entire process is repeated. So now window would be at this location. Now my central pixel has changed, my surrounding pixels have changed, and I will calculate the new value of the new central pixel. Like this, one by one, all the brightness value of the pixels are calculated and the new image, the filtered image, is generated. So like this, one by one, the pixel till the last pixel is achieved. Okay, so here I have shown a subset of an image. So the brightness values also I have marked here. So suppose I take this particular pixel and this particular window mask. This window mask is having 0, 1, 0, 1, 1, 1, 0, 1, 0 values. So when I calculate the brightness value, it is coming out to be 186. Okay, so that would be replaced by the central pixel value. So you can see before filtering how the image was appearing, and after filtering how the image would appear. So based on the operation that is performed, there are two types of filters: low pass filters and high pass filters. Low pass filters, they block the high frequency details and have a smoothing effect on the image. They are used for removal of noise and removal of salt and pepper effect from the image. When we apply the low pass filter, the edges are blurred. Edges in the images get blurred. So you can see here, this is on the right hand side, the low pass filtering is done. So the smoothened image is generated. The high pass filters, they preserve the high frequency and removes the slowly varying components. They emphasize the fine details. They are used for edge detection and enhancement. And edges, as we have already discussed, are the location where transition from one category to another happens. So when we apply the high pass filter on the same image, you can see that the edges are now more pronounced. These are some of the low pass filters: mean filter and average filter. So as you go on increasing the window size, the effect of the filtering goes on increasing. this is median filter. We can calculate the median within that particular kernel. And mode filter. Okay. These are again low pass filtered images. The high pass filtering again is divided into two types based on what type of filter you are using. It can be linear and non-linear. In the linear high pass filtering, the output brightness value is a function of linear combination of brightness values located in a particular spatial pattern around the input image. Okay, whereas in the non-linear high pass filtering, it is a non-linear combination of pixels. High pass filters can also be divided classified based on whether the background is what type of filtering it is doing. So we can have edge detection or edge enhancement filter. In the edge detection filters, only the edges are remaining and the background is lost. In the edge enhancement filters, they delineate the edges and makes the details more prominent, whereas the background would not be lost. Edge detection filters are also zero-sum kernels. That means if you sum up the values of the kernel, you will find a 0. Okay, so the sum of all the coefficients in the kernel equals 0. This generally causes the output values to be, this generally causes that if there is an edge, it will detect the edge, and if the edge is not there, the homogeneous area is there, then it will make its spatial frequency as 0. That is why it is coming as black in color. So an edge detector smooths out or zeros all areas of low spatial frequency. It creates a sharp contrast where spatial frequency is high. So now the resulting image only has zeros and the edges. So we can also create zero-sum kernels in a particular direction also. And such type of kernels are called as directional filters also. So this is an example of edge detection. So the original image, 3x3 edge detector, and when we increase the size of the kernel, more edges are now getting detected. The second type of high pass filters are edge enhancement filters. They highlight the edges but do not eliminate other features. So the sum of the coefficients of kernel is not 0. As I have shown you an example of the kernel, here the sum of the coefficient of kernel is not 0. So when such type of kernel is used on a set of pixels in which a relatively low value is surrounded by high values, so what will happen? The low value will become further low, the high value would become further high, or what we can say, the edge would be enhanced, whereas the background would not be lost. Okay, so this would be the effect of edge enhancement filter on the image. So certain filters such as Laplace filters, they are very important. So I have shown you the kernel of Laplace edge detector and edge enhancer also. So the Laplace operator highlights point, line and edges. So you can also design edge detectors in a particular direction. So if you want to enhance edge in a particular direction, you have to give more weightage to the kernels of that direction. So as here in this case, if you want to create a horizontal filter, so in the horizontal line has to be given more weightage, whereas the other values have to be given negative weightage. Similarly, diagonal, vertical, and you can also make these filters in different directions, such as north filter, northeast filter, and so on. So in various application where you have to extract certain edges trending in a particular direction, then you can go for such type of directional filters. Now coming to non-directional edge enhancement filters, the first one is Sobel filter. Okay, so this is the expression for Sobel filter. The output for Sobel filter would be square root of x square plus y square, where x is brightness value 3 plus 2 into brightness value 6 plus brightness value 9 minus brightness value 1 plus 2 into brightness value 4 and plus brightness value 7. Or what we can say is it will apply two filters simultaneously, two 3x3 filter, one for x, one for y, and the output of this x plus y in form of square root of x square plus y square would give us the central pixel value. So this is Sobel filter. And these are the results of Sobel filter. Okay, you can see so many edges have been extracted. Another filter is Roberts edge detector. So in Roberts edge detector, again, we have two different filters. One is X and one is Y. But in this, X is only brightness value 5 minus 9 and Y is 6 minus 8. So simply two filters are applied and the output is generated. So you can see this is Roberts outputs from Roberts edge detection. Okay. These are again some of the outputs for different images. Then we have this Kirsch filter. We will not go into the details of Kirsch filter. You can just understand that there is another non-linear enhancement filter which we call as Kirsch filter. Okay, then the third type of image enhancement is spectral enhancement, or we call them image transformations also. So in spectral enhancement, the output brightness value is calculated by taking the brightness value of pixel in multiple bands. Okay, so image transformations typically involve manipulation of multiple bands of data, whether from a single multispectral image or from two or more images of same area acquired at different time. So either way, image transformations generate new images from two or more sources, and this highlights the particular feature or properties better than the original input images. A very common type of image transformation is image division, or we also call it as band ratio. Band ratio, on a pixel by pixel basis, the band 1 values are divided by second band so as to generate a new band. So now whatever are the new brightness, new values that we have obtained after division of, after ratioing of band 1 and band 2, we fit them into these 0 to 255 using minimum maximum stretching. So now why do we apply these ratios? So if you see if we are having the similar type of vegetation on two types of the hill, one on sunlit side and one on the shadow side, it will become very difficult for us to, for our computer to identify such similar vegetation on two different illuminated areas, because of this sun illumination, solar illumination, the pixel values, the brightness values are completely different, as you can see here. For deciduous trees in the sunlit area, the values are something around 48, whereas in the shadow area, the values are 18. Okay, but when we take an average between band A and band B, in the sunlit and shadow area, the values range is similar. Okay, so because of this, we can say that it is able to reduce the undesirable effect of topography on the recorded radiances, and we are able to identify or distinguish the features properly in the sunlit and in different illuminated condition also. So these are the applications of ratios. The when we are applying ratios, which bands should we ratio? It depends on what feature we are going to extract. So suppose we want to extract vegetation. So look at the spectral reflectance curve of vegetation. It shows a dip in the red part and a peak in the near infrared band. So if we take a ratio of infrared by red, the values would be highly pronounced than the other ground surface features. Okay, so ratios, they portray the variation of slope of a spectral reflectance curve between two bands which are involved. So such type of analysis has to be done before doing ratio images. Okay, so using the theoretical knowledge about the spectral properties of rocks and minerals, so this author, they have chosen certain ratios for iron oxides and for hydroxyl bearing minerals, and they have identified iron oxide areas and hydroxyl minerals also. Okay, so similarly here also, these are the individual ratio images. The various features are enhanced, and here at the other side of the image, we have the infrared and red of the area, and when we divide, we calculate the ratio infrared by red, the entire vegetation part is so pronounced. So these are some of the commonly used vegetation index, but it will depend on which particular feature you are you want to highlight. So if you want to highlight water, so there are certain ratios for water. If you want to highlight the buildings, so different ratios are available for buildings and urban area also. Okay. Now, the second type of image transform is principal component analysis. So as we understand that different bands of multispectral data are often highly correlated and thus contain similar information. So we need to transform the original satellite bands into new bands that express the greatest amount of variance from feature space of the original bands. The objective of this transformation is to reduce the dimensionality in the data and compress as much information in the original bands into fewer number of bands. So these new bands that are coming out of this statistical procedure are called as components, and this process attempts to maximize the amount of information from original data into least number of new components. component. So as you can see, if you plot a scatter plot of your data, if your data is having correlation, so ellipse sort of thing would be appearing, whereas if it is non-correlated, this is how the data would look like, the scatter plot would look like. So if the data is correlated, we would apply PCA on such type of data so as to uncorrelate this data. So to apply PCA, first of all, what we will do is we will take the mean of band 1 and mean of band 2. Okay, if we are talking only about only for 2-band data. So we will take mean of band 1, mean of band 2. We will take the intersection of these means and shift our origin to this particular intersection of means. So what we will do is, to apply PCA transformation, we will find the mean of each band and shift the origin to the intersection of these two means. So you can see we have shifted the means, the origin to the intersection of the means. After that, we will translate the axis system so that the first axis lies in the direction of maximum information. So direction of maximum information is the longer axis of the ellipse, and the second axis would now lie in the direction so as in the second axis of the ellipse, in the minor axis of the ellipse. So the minor axis of the ellipse contains the information that is originally not picked up by the longer axis. Okay, so now the original brightness values are redistributed or recalculated, so using this particular axis system. Okay, now when we plot the new brightness values, we will see that these new brightness values are uncorrelated and the scattergram loses its elliptical shape. Okay, so now the x-axis is the first principal component, which is giving us the maximum information because it was taken in the direction of longer axis of the ellipse. The second principal component gives us the information which is not available in the first principal component, unique information, because it is at 90 degree to the principal component 1. So these are the, for the 6-band data, the principal component analysis was carried out. You can see in the first principal component, the maximum amount of information is available. The second principal component shows us the information that is not available in first principal component, and so on. So till the last pixel principal component, only the noise is available. Okay, so for our Ponta data, this is principal component 1, 2, and 3. We can generate a color composite of this principal component also. So we can leave out the noisy components and use the principal components only in which there is the information content is there, and then we can do an inverse principal component analysis and go back to RGB space, thereby reducing the dimensionality of data and reducing the correlation between the components. Okay, so this is all from my side. You can post your questions. We will